Work, energy and power is one of those topics that are usually a little bit more challenging in the question papers. The good news though is that you will be able to collect quite a substantial amount of marks without being able to solve all the problems. In this first module, we're going to look at energy that you've already done in grade 10, and then we will also look at solving work problems. Hierdie onderwerp is ook beskikbaar in Afrikaans. In this module, we're going to look at the definitions of energy and of work, and then we will also briefly look at the calculations that you've done in grade 10 on energy, and we will see how we're going to use the work definition to enable us to solve work problems. We define energy as the ability to perform work. Now, you've learned in grade 10 that the kinetic energy of an object is that energy due to its motion. We use the abbreviations EK or capital K for kinetic energy, and the formula that we use is EK is equal to half mv squared, where EK represents the kinetic energy in joule, m is the mass in kilogram, and v is the velocity in meters per second. You have also learned that the potential energy of an object is the energy due to its position. We use the abbreviations EP or capital U, and the formula EP is equal to mgh, where EP represents the potential energy in joule, m the mass in kilogram, g the acceleration or gravitational acceleration in meters per second squared, and h the height in meters. The third type of energy that you've learned about is mechanical energy. And you will remember that mechanical energy is the sum of the potential and the kinetic energy at any specific position. So what does all of this mean? If you have a trolley that's running on a frictionless trolley track, we will be able to calculate the potential energy, the kinetic energy, and the mechanical energy of this trolley on this trolley track. So if we consider the initial position where the trolley has a velocity of 0 because it starts from rest, the potential energy will be the mass of the trolley, which is 2, times by gravitational acceleration of 9.8, times by the initial height, which is 5 meters. And that gives us a potential energy of 98 joule. But because the initial velocity is 0, the kinetic energy of the trolley at the initial position will be 0. And therefore the mechanical energy, which is the sum of the potential and the kinetic energy at that specific point, is 98 plus 0, which is 98 joules. Now if we ignore all types of friction, the trolley will convert its potential energy gradually into kinetic energy as it runs along this track. So we will be able to calculate the potential kinetic and mechanical energy of this trolley at any specific point on this track if we know what the height of the trolley is and the velocity of this trolley. So at this new position where it's got a height of 3 meters and a velocity of 6,261 meters per second, the potential energy will be calculated as 2 times 9.8 times by the new height of 3 meters, which will give you a potential energy of 58.8 joule. The new kinetic energy is now half times by the mass, which is 2, times by the velocity of the trolley at this position, which is 6,261, and then really important to remember that you have to square the velocity. And that gives you a final answer of kinetic energy, which is 39.2 joules. The mechanical energy, which is the sum of the potential and the kinetic energy, should be conserved because there's no friction involved. So if we look at the sum of the potential and the kinetic energy, it is still 98 joules. So if we consider the trolley at the bottom of the track, The potential energy of this trolley should be zero because it doesn't have a height anymore. But the kinetic energy should be at a maximum because all the potential energy that this trolley had at the beginning would have been converted into kinetic energy. But the mechanical energy should still be constant because there's no friction involved, and we know that mechanical energy should be conserved if there's no friction. So let's look at the calculations. The potential energy, because the height is 0, will be 0 joule. The kinetic energy is a half times 2 times by the velocity squared, which is 98 joules. And then the mechanical energy is the sum of the potential and the kinetic energy, and that gives us 98 joule. That brings us to the definition of work. Now, if my job is to move a desk, and the desk is still at exactly the same position after an hour, I will not receive any compensation for my work. So for work to be done, we need an applied force and a displacement of the object in the direction of that force. So the definition for work is the product of force and displacement with the force in the direction of the displacement. And if we look at the symbols of the formula, the capital W represents work in joule, the capital F is the force in Newton, delta X is the displacement in meters, and then we multiply this by the cos of an angle. Now this angle is the angle between the force that we use and the displacement of the object. It is important to note the units that we use for this formula. You have already seen that work is measured in joule, and we know that force is measured in newtons while displacement is meter. So joule is the same as Newton meter. It's also important to know that work is a scalar quantity. If we multiply a vector by a vector, we will always get a scalar quantity as an answer. So force, which is a vector, times by displacement, which is also a vector, will give us work, which is a scalar quantity. This will mean that you will never include a direction for the answers to your work calculations. Now let's consider different situations where we will be using this formula. In the first case, we have a man that applies a force to a desk, and the desk will then move in the same direction as the applied force. So if we look at the formula, which is W is equal to F delta X, then the force and the displacement are both in the same direction. So the angle that we're going to measure between the force and the displacement will be 0 degrees, and the cos of 0 degrees is 1. So let's look at an example of a calculation where the applied force and the displacement are both in the same direction. A brick is pushed for 2 meters across a horizontal cement floor with a horizontal force of 3 Newton. The frictional force is 0.4 Newton. Calculate the work done by the 3 Newton force on the brick. Now it's important to note here that they're asking you for the work done by the 3 Newton force. Therefore, when you substitute the force into the formula, it will only be the 3 Newton force that you substitute, and you will ignore the frictional force. So therefore, the work done is 3 times the displacement of 2 times by the cos of the angle between the force and the displacement. And in this case, the force and the displacement are both in the same direction. Therefore, the angle between the force and displacement is 0 degrees, and that gives us an answer of 6 joule. Now you'll remember that work is a scalar quantity, so no direction is indicated. The second situation is where the applied force and the displacement of the object are not in the same direction. In the illustration, you can see that the force is applied at an angle and that the object will move in the direction of the horizontal component of the force. When we substitute the values, we will use the horizontal component of the applied force and the displacement, because we know that the horizontal component and the displacement are both in the same direction, and therefore we can use the cos of 0 degrees again. You may, however, use the original force given to you, but then you will have to substitute the angle between that applied force and the displacement of the object. This will complicate some of your calculations, especially if you have to calculate the net work done. So I would rather recommend that you use this method where you first calculate the horizontal component of the applied force and then substitute the cos of 0 degrees. I will show you how to do this in the following example. A wooden box with pebbles is pulled across a horizontal cement floor with a force of 30 Newton. The rope that is used to pull the box makes an angle of 60 degrees with the floor. The frictional force is 0.4 Newton. Calculate the work done by the applied force onto the wooden box. Now, if we consider a force diagram, we will see that there's a force of 30 Newton applied to the box at an angle of 60 degrees. And there's also frictional force of 0.4 Newton. So if we have to calculate the work done by the applied force, the first step would be to calculate the horizontal component of the applied force. So in the diagram you can see that we will calculate the adjacent side of the triangle, therefore we will use the cos of 60 degrees. So substitute the horizontal component of the force, which is the applied force of 30 Newton times by the cos of 60 degrees times by the displacement of 2 meters. And because we know that the horizontal component and the displacement are both in the same direction, we can substitute a cos of 0 degrees. And that will give us an answer of 30 joule. You may, however, use the applied force of 30 Newton as the force in the formula and the displacement of 2 meter, but then you have to use the angle between the applied force and the displacement, which is 60 degrees, and that will also give you an answer of 30 joule. I did, however, recommend the first option, because when we have to calculate the net work at a later stage, it will just be easier to use the first option where we have to calculate the horizontal component of the force first. Now we will look at a situation where the applied force does not have any components in the same direction as the displacement. In the illustration we have an ant that applies a force upward onto the food, but the food will move with the ant, and the displacement will be at a perpendicular angle to the applied force. So when we substitute the values into the formula, we will substitute an angle of 90 degrees, and that will give us work done by the applied force of 0 joule. Now this happens because the applied force does not contribute to the movement or the displacement of the food. Other forces cause the displacement of the food, and therefore the work done by the applied force is 0 joule. We are back with our example of the wooden box, and now they ask us how much work is done by gravity. Now gravity is perpendicular to the displacement of the box. Therefore we know that the work done by gravity will be 0 joule, because gravity is perpendicular to the displacement of the box. So what will we do in a situation where the force and the displacement are opposite to each other? So in the diagram you can see that these men are all pulling in one direction, but obviously they are moving in the opposite direction. So if we consider a force and a displacement that are opposite to each other, we have to substitute an angle of 180 degrees. That means that the answer will be a negative answer. But we know that work is not a vector. So what does a negative answer for work actually means? Negative work is when the total energy of a system decreases. An example will be the brakes of a vehicle that will decrease the total energy of the system because negative work is done onto the system. Another example will be friction, because friction is always opposite to the displacement of an object. Therefore, friction will also always do negative work. We are back with our example of the brick with a frictional force of 0.4 Newton, but now I ask you to calculate the work done by the frictional force onto the brick. Now, if we have to calculate the work done by friction, we will substitute the frictional force into the formula. So the work done is the frictional force of 0.4 Newton times by the displacement of 2 meters, but now the angle between the friction and the displacement is 180 degrees. And that gives us a negative answer. And we already know that a negative answer for work means that the total energy of the system is decreased by that amount. In this situation, it is gravity that causes the man to ski down the slope. So again, we have a situation where the force and the displacement of the object are not in the same direction. So again, we will work with a component of the force which is in the same direction as the displacement of the object. So in this case, we will work with a parallel component of gravity. And we will substitute the parallel component of gravity into the formula because we know that the angle between this component and the displacement of the object will be 0 degrees. A tractor has a mass of 800 kg and slides 3 meters down a 20-degree slope due to the effect of gravity. Calculate the work done by gravity onto the tractor. Now, if you consider a force diagram, you can see that we will have to go and calculate the parallel component of the weight in order to get the component that is in the same direction as the displacement of the tractor. That will mean that we will need the sin of 20 degree in our calculation. So in the formula, the parallel component of the weight is the weight of 800 times 9.8 times by the sin of 20 degrees to get the parallel component, times by 3 to get the displacement, times by the cos of 0 degrees, because we know that the displacement and the parallel component of the weight are both in the same direction. And that will give us work done of 8,044.31 joule. In this example, we have a man that applies a force to a mass piece in order to move it up an incline. But gravity will pull the mass piece down. So again, we have a force and a displacement that are not in the same direction. So we will work with the parallel component of the weight again, because we know that the parallel component of the weight is in the opposite direction to the displacement of the object. So when we substitute the values into the formula, we will use an angle of 180 degrees again, and that will mean that gravity will do negative work. So in this example, the man will do positive work to move the mass piece up the incline, but gravity will do negative work as it will take energy from the system. A man on his bicycle has a combined mass of 110 kg. The man rides his bicycle up a 100-meter slope with an incline of 30 degrees. He applies a force of 1,000 Newton to move up the slope at a constant velocity. Calculate the work done by gravity on the cyclist and his bicycle during the 100-meter ride. So if we look at the force diagram, you can see that we will have to go and calculate the parallel component of gravity in order to get a force that is either in the same direction as the displacement or opposite to the displacement. So we will use the sin of 30 degrees in order to get the parallel component of the weight, and we will substitute that into our formula. So the weight is 110 times 9.8. To get the parallel component of the weight, we multiply that by the sin of 30 degrees, multiply by 100, which is the displacement, multiply by the cos of 180 degrees, because the displacement and the parallel component of weight are opposite to each other. And that will give us negative work done by gravity of 53,900 joule. If you are an educator that would like to inquire about the use of these PowerPoint slideshows in your classroom, you may contact me at lawsandwonders@gmail.com. Please indicate if this topic was useful to you or not, and subscribe to my YouTube channel in order to stay informed about the release of my most recent videos.